Right. Let's go over this. Okay, so what we have here, which we haven't really dealt with before, is a secondary electrophile. Specifically a secondary, in this case, benzylic chloride, right? So the chloride is what we call in the benzylic position relative to the benzene ring or to the phenyl group. Then we're treating that with potassium cyanide in dimethyl formaldehyde. Obviously, it's going to be a substitution reaction. Right? What's the product going to look like?
Is it just going to be the CN replaces the Cl?
Good. Which direction is it going to be going? You know?
It's going to become a wedge.
Good. All right, so that's going to be the product. So when we look at this reaction, right, we said it's secondary electrophile, and we know that secondary electrophiles, particularly benzylic electrophiles, can undergo both SN1 and SN2 pathways, or proceed through SN1 and SN2 pathways when they undergo substitution. What do you think the major pathway is going to be here? What's the major mechanistic pathway that's going to follow here?
Would it be like SN2 because KCN is a strong
Because line? Say it again.
Wait.
So how many people think it's SN2? Just raise your hand. How many people think SN1? Okay, all right, so why do y'all think it's SN2? What are some of the things that point to this being SN2?
Well, I feel like the salt's going to dissociate, so you're going to have a really strong neutral nucleophile.
The potassium cyanide?
Yeah.
Okay, so we have a pretty good nucleophile, right? So the other day we said that mostly SN1 reactions are going to occur under solvolysis conditions, right? So these are not solvolysis conditions. So we have a pretty good nucleophile. All right, what else points us in that direction?
The DMX solvent is polar and lowering the energy of
Good, so we're using an aprotic solvent, right? So that's going to help promote an SN2 pathway over an SN1 pathway, right? That can't, again, that's not the only factor that you can look at, right? I would say that's among the least important things, but that's something that we can do to kind of help one pathway favor another pathway. Right, what's something else? Yeah.
The chlorine would not be good in here by itself.
Awesome. Yeah. So the other thing that we have here is chloride, which is not the best leaving group, right? It's not a bad leaving group, right? But if we're setting up an SN1 mechanism or an SN1 reaction, we would want something that, when it leaves, right, it's going to be a really good, really stable leaving group, something like iodide, something like water, right? That we can make through an acid protonation of alcohol. So we'll just say this is an okay leaving group. Right, so those three things, right, because we can't, by looking at the electrophile, judge on our own, right? Usually we can just take a look at the electrophile and say this is a tertiary electrophile, it's got to go through a unimolecular mechanism, right? This is a primary electrophile, it goes probably through a bimolecular mechanism. Secondary, it's on the edge, we can go either way, right? So we have to look at these other factors. Okay. Any questions on getting that product? Okay, we'll talk about the stereochemistry here in a little bit. Okay, draw the transition structure. So remember, the transition structures just show the bonds that are being made and bonds that are being broken, right? And then any charges that are either disappearing, right? Charges that we are losing going from the starting material to the product, right? Or any charges that are being formed as we go from the starting material to the product. Right, so I'm going to redraw my starting material in a slightly different way. Right, so that's going to be the same structure. Stereochemistry is going to be exactly the same as well, right? All I'm doing is just kind of turning it around so the chloride and the phenyl group are in the plane, of the board, right? And the hydrogen and the methyl group are out of the plane. So I'm going to use that structure in my transition structure. The stereochemistry in this reaction is going to be important. All right, so here's my transition structure. You can see I'm breaking the carbon-chlorine bond, same time as I'm making the carbon-carbon bond from the cyanide nucleophile, right? And then I've drawn this transition structure to show or reflect the stereochemistry of that starting material, right? So the hydrogen is, all three of these are kind of in a plane that's perpendicular to the board, right? Hydrogen is coming forward, methyl group is going back, and the phenyl group is going down. And so this is what I want you to pay attention to. Right, so remember, whenever the nucleophile adds in an SN2 reaction, it's got to interact with the anti-bonding orbital of the carbon-leaving group bond, right? So it's kind of, these red markers are always crap. The nucleophile, when it comes in, it has to undergo backside attack. Okay, and so it's always going to be adding to the opposite side of the carbon-leaving group bond, right? You can see our three other groups, the phenyl group, the hydrogen, and the methyl group, they're all kind of pointed in this direction, right? And in the end, all three of those groups are in the same orientation, right? The methyl group's still going back, hydrogen's still coming forward, phenyl group is still in the plane, but now they're tilted in the opposite direction. Okay, and what is happening here is whenever you do an SN2 reaction, you get what's called stereo inversion, right? So if the nucleophile, if the leaving group is hashed in one structure, right, the nucleophile that replaces it is going to be wedged in the product structure, right? Often this results, or most of the time this results in a change of an RNS stereochemistry, right? So if the starting material is R, the product will be S. But that's not always the case, right? Because RNS is just our way of communicating with each other, and it depends upon the priority of the groups, right? So if the leaving group is the first priority group in the starting material, and the nucleophile ends up being the second priority group in the product, right, then we might not change RNS stereochemistry, okay? Even though we're still getting that inversion, right? Even though the starting material will be a hash, the product will be a wedge, right? The actual RNS, the way that we name them, might not be any different, right? So just keep that in mind, that the stereo inversion occurs, but RNS might not always switch. Usually it does, right? Usually the nucleophile is the high priority group, right? And the leaving group is the high priority group, or whatever, right? We don't change the priority. But if the priority somehow changes in the course of the reaction, right, then the RNS stereochemistry might not change. Okay, there's a problem like that in my problem set, if you want to take a look at it. Okay, but this transition state, I think, really shows, if we compare the starting material to the product, right, it shows how we get that stereo inversion, right? In the starting material, these three groups are leaning off to the left. In the product, those three groups are leaning off to the right. And we have to do a complete backside attack, right, to get rid of our leaving group in SN2. Any questions about that? Anybody want to suggest reagents and conditions to get from the nitrile to the amine? Joe?
I'm not sure if I'm thinking too hard, but do we need to use a Grignard?
So you're on the right track, but if you look at what is being added, let me draw this up here. All right, what atoms are being added to the carbon to get to the?
Oh, okay, I see. So the leaving group isn't the cyanide.
No. So if you look here, we have carbon, carbon, nitrogen. We still have those same three atoms.
Could we do a reduction?
Suggest a reagent.
I guess lithium, aluminum hydride.
Good. Right, so Grignard addition would also be reduction, right? And if we could add Grignards to nitriles, but we would get carbon groups in that position rather than hydrogen groups, right? So then it suggests we would use lithium aluminum hydride. Usually do that in some ethereal solvent, so we'll just suggest THF as the solvent. And then the second step will work up the reaction with, just say, water. And that will provide the protons that end up on nitrogen. All right, this is an example of a reductive elimination, or reductive amination. This is a term we talked about last semester, describes any reaction that forms amines through reduction. Right, so this is one example of a reductive amination. All right, and then final one is assigning R and S stereochemistry. Cal, you want to tackle this one? Right, so why don't we start with the starting material? Right, the first thing we'll do is assign priority. So how would we assign priority? I'll put all of the atoms here.
So chloride would be 1.
Great.
Then phenol would be 2.
Good.
And then methyl is 3.
Good. And then the hydrogen is 4. Okay. So what would this be? Some of the hydrogen's coming out toward you, right? So this is a good one that you can use the thumb method for.
This would be X.
Good. Yeah. People agree? S. Yeah.
I
You agree? Yeah. Right. So if we use the thumb method, remember the thumb represents the low priority group. You're pointing your thumb in the direction, whatever direction that low priority group is going. Right? If your fingers on your left hand curve in the order of the other priorities, right, then it's going to be an S stereocenter. If your fingers on the right hand curve in the order of the other priorities, then it's going to be an R stereocenter, right? So you can see hydrogen's coming out. My left fingers go from 1 to 2 to 3, right? They're curving in a clockwise direction. So we would name this the S stereocenter, right? And in this case, this is an example where we are going to switch R and S stereochemistry, right? So the product is going to be an R stereocenter. Same thing here, right? If this is coming out, that's also going to be the R stereocenter. questions about this? All right, so let's switch up this reaction just a little bit, change the conditions. You use the same starting material, so the benzoyl chloride. What we're going to do is we're going to add into this reaction 5% sodium iodide. Right, so the limiting reagent is 1 millimole, right? Or say the limiting reagent is 10 millimoles, right? 5%, we're just adding in 0.5 millimoles of the sodium iodide. Right, so not enough to actually make the iodide product. Right, when we do this, you can see the chloride in the starting material is a hash, right? The nucleophile that we're replacing with, the cyanide, is also a hash. So what's going on here? Evan, yeah.
Is the iodide replacing the chloride, and then the cyanide group is replacing the iodide, so it like switches one way and then switches back?
Why would that make sense?
Because the iodide is like it's a stronger leaving group, and also it's stronger to tack into, so it would want to replace the chloride, but then it would immediately want to leave because the cyanide is stronger than that, so then it would get replaced by that.
Excellent. Right, so the other day we talked about how iodide's kind of weird, right? Because it's the best leaving group, or among the best leaving groups, right? But it's also among the best nucleophiles. Really good at doing nucleophilic substitution on a saturated carbon. Right, so in this reaction we have 2 nucleophiles. We have the iodide and we have the cyanide. Right, so the fastest reaction that's going to occur is going to be between the better nucleophile, right, and the electrophile, rather than the cyanide and the electrophile. So the first thing that will happen is we'll get to our iodide. We can only make 5% of this though, right, at any one time. That's the maximum amount that we can make. When we do that, we still have the cyanide in the reaction, right? And now we have this really, really hot electrophile with a really good leaving group. Right, so that cyanide come in, replace the iodide. And so this is undergoing 2 stereo inversions, right? The iodide does the stereo inversion first, right? And then switches back to the hash after the cyanide adds.
So I think I'm just a little bit confused still about the stereo inversion.
Yeah.
So when does it happen and when does it not happen? Because between the second transition state in our first example, it didn't switch back.
Right, so here, right, we only have 1 nucleophile, right, just the potassium cyanide. So the only thing that can happen is the cyanide come in, kick out the chloride, and we make the product, right? And so that's going to result in a stereo inversion.
Yes.
It's got to undergo backside attack. Here, that stereo inversion is still happening, right, but we have 2 nucleophiles. One is better than the other, right, and it just so happens that the better nucleophile is also a really good leaving group. Right, so that stereo inversion is going to happen here, right, because of the iodide. And then when the cyanide gets enough encouraged to add, right, it's gonna undergo that second stereo inversion. So the product, right, the net, it's still a stereo specific reaction. We're only making one enantiomer, right? But because it's undergoing two substitutions, right, we get kind of back to where we started.
So because there was no like leaving group in the second transition state of the first example, like it was just a reduction with the hydrogens they did.
Yeah, over here?
Yeah.
Yeah, so whenever we're doing substitution, right, that substitution's occurring on that carbon, right? The
Yes.
carbon of the, with the stereo center. Whenever we're doing reduction, those hydrides are being added to this carbon, right? We're not doing anything to the carbon with the stereo center. Other questions?
Can I ask a question about
Sure.
when we did the reductive animation?
Yeah.
It's more important that we use the lithium and the aluminum hydride instead of like boron hydride, right?
Correct, yeah. So borhydrite's not going to be able to reduce nitriles. They're not electrophilic enough to.
So it's more important because the lithium and aluminum hydride is more nucleophilic.
That's a lot hotter of a losing agent. You all actually get a chance to use LAH, aluminum hydride, this semester. So. Other questions? So we looked a little bit, just to kind of close the loop, we looked a little bit about at the stereochemistry of SN1 reactions, but just to review what's going to happen. So we'll take our same secondary electrophile. Right, this time we'll set it up so it undergoes a unimolecular reaction. Okay, so we'll have in there a really good leaving group, say a put in there a triflate leaving group. So this is one of the sulfonate leaving groups we looked at the other day. Great, you have a question?
It
Yeah,
might be
sure.
silly, but
It's fine.
for the second two like products, where you assign R,
Here.
yeah, and the one before that too.
Yeah.
Did we just know that that was R, or did you like?
So
assign-
I didn't go through the process,
Right.
but we can do that if you want.
Okay, yeah.
Yeah. I did that because I know that chloride is the high priority leaving group here. Cyanide is going to be the high priority leaving group here, and all the other priorities are going to stay the same. So if this is S, chloride's going back into the board, or the high priority group's going back into the board. Here, the high priority group's coming out of the board, so that's going to be R. Okay. But let's go through those priorities really quickly. Right, so it helps whenever you're doing the assigning priority or assigning RNS with all four substituents around that chiral center. Okay, and so when we look at this, we have a carbon, and a carbon, right? So when we're assigning priority, right, we're going to say, what is the highest priority atom attached to this carbon, highest priority atom attached to that carbon, highest priority atom attached to that carbon. And this one's easy because we can get that difference right away, right? So highest priority atom attached to this carbon is nitrogen. Highest priority atom attached to this carbon is another carbon. Highest priority atom attached to that carbon is a hydrogen, right? So that just is going to be 1, phenyl group will be 2, and then the methyl group will be 3, and then the hydrogen will be 4. When we went over stereochemistry last semester, right, I said that if the high priority group is a hash, right, if it's oriented to the back of the board, all we have to do is look at the other groups, and if they're ordered clockwise, then it's R. If they're ordered counterclockwise, then it's S, right? So here they're ordered clockwise, 1 to 2, 2 to 3, and so that will be the R stereo center, right? Same thing here, right? The 2 hydrogens that we're adding don't change the fact that this carbon is still bonded to a nitrogen, right? So it still gets the high priority assignment. So 1, 2, 3, 4. questions about that? Okay. Not a bad idea. I mean, so the substitution, elimination, the addition chemistry that we're going to go over in chapter 15. It's pretty important that you know stereochemistry and that you can assign stereochemistry. So if you do need practice with that, I would recommend going back to chapter 11, I guess it is, taking a look at stereochemistry. Okay, so if we take a similar secondary electrophile, right, but we're going to change the leaving group. So triflates, this sulfonate group, it's called a triflate. You can imagine, because we have 3 fluorines on a carbon, whenever this leaves, the negative charge on the oxygen that is leaving is going to be really stabilized because of the inductive effect, right? That fluoride, those fluorines are going to be able to pull electron density away from this part of the molecule, distribute it, right, and make it a better leaving group. Triflates are on the order of iodide in terms of leaving group ability. Okay, so we have a really good leaving group, secondary electrophile, okay, and then we're using an alcohol as a solvent, so a really crappy nucleophile, right, but one that is set up for solvolysis. So whenever this reaction occurs, it's likely going to occur through a unimolecular pathway, right? SN1 substitution. And because this is happening through a unimolecular pathway, it's going to result in a racemic mixture of enantiomers.
So do we know it's SN1 because it's solvolysis or because it's a crappy level?
So it's kind of all of these, right? So the fact that methanol can be the nucleophile and the solvent, right? So it's a polar protic solvent. Right, it's also a core nucleophile. Secondary center, right? And we have a really good leaving group. So all 4 of those factors we have to take into consideration and say this is probably going to go through SN1. Does that make sense? Yeah. Other questions about that? Okay, so the reason why this would result in the racemization of the stereocenter, right, which is bad. We chemists typically don't go through the work of getting a starting material that has that is enantiopure, right, that is one enantiomer, and then destroy that stereochemistry in a reaction. We try to avoid that because those stereocenters are usually very valuable and can be difficult to form if we're not just buying them from a company. So mechanistically what's happening is in the first step, triflate's going to leave, right? We don't have a good nucleophile to come in and kick it out. We're going to form this carbocation intermediate. It's somewhat stabilized because it's in conjugation, that empty orbital is in conjugation with the benzene ring, right? So the benzene ring can add into that empty orbital to help stabilize the charge. Excuse me. right? But we have to think about what this looks like in 3 dimensions, right? This is a trigonal planar center. And that positive charge is reflected by an empty 2p orbital on carbon. So when the nucleophile adds methanol, right, it can either add from the top face, which is the re face, right, or it can add from the bottom face, which is the side face. Right, addition to the side face is going to lead to, let's see here. It's going to lead to the S stereo center. Addition to the reface is going to lead to the R stereo center. Right. And there's no like code for figuring that out. It's just a matter of kind of seeing it in 3 dimensions. If you need to build a model, you can build a model. Right. But understanding that there's a 50-50 shot of going from the top face to the bottom face, and so we're going to get a 1-to-1 mixture of enantiomers. Right, kill that stereochemistry that we started with. Yeah.
The reface will be R or S?
So the reface is, in this case, the reface is going to lead to R. Addition to the reface is going to lead to R. Addition to the side face is going to lead to S. That's not always going to be the case, right? Just that's unique to this example. Questions?
What's the opposite of a racemic mixture?
What's that?
Yeah, you said racemic earlier.
Racemic, yeah,
Racemic.
racemic mixture. It's just a 1-to-1 mixture of enantiomers. That's all that means, yeah. Yeah,
So
sir.
reface is just the top, the side face is the bottom.
So in this case, let me draw it out. Do you see this here? Okay. So we can name re and side face just like we name R and S. It's actually a little bit easier. So all we have to do is assign priority to 3 groups. In this case, the phenyl will be the 1, methyl will be 2, and the hydrogen will be 3, right? And if that order goes in the clockwise direction as we're looking at it, right, it would be the re phase, right? And if it goes in the counterclockwise direction, it will be the side phase. Yeah. Again, this is just a way, if I tell you to draw a carbonyl, right, or any trigonal planar center so that the reface is pointing towards you, right? This is just how we communicate with each other, just like R and S, right? Not an innate property of any molecule. Other questions? Maybe we move on. so this is going to get us talking more about elimination. As we go through elimination, we'll be comparing it to substitution, right? The same conditions that affect elimination are often the ones that also affect or can affect substitution. So you've seen some elimination reactions before. So if we take say an acid chloride, treat that with sodium hydroxide. Right, that results in the substitution to give us ultimately a carboxylic acid after some workup. Right, so I'll have more arrows in there because this, if we have sodium hydroxide, carboxylic acid is not going to stick around, right? We're going to have to, it'll deprotonate, then we'll have to reprotonate. Okay, but you can see whenever we do this addition, this is a net addition, it occurs through two steps, right? So, or sorry, it's a net substitution, but it occurs through two steps. First step being addition, right? Second step being elimination. Right? You can see in that elimination, we're forming a pi bond. Right? And we're doing that by kicking out a leaving group. So you've seen elimination reactions before, right? So these are not new, we're just kind of doing them on slightly different systems. Okay, so if we take our benzoyl chloride that we started with at the beginning of the lecture, and we change up the conditions of this reaction, so rather than treating it with cyanide, we're going to treat it with potassium terpbutoxide. And we'll do this in terpbutanol, right? So the alcohol version, or the protonated version. And we're also going to heat this up. Right, so we're going to reflux it. Main product, the major product that we're going to get is going to be E2 elimination product. Okay, so just real quick, mechanistically, what's going on? The alcohol or the alkoxide that we're adding is going to act as a base, right? And there are a couple reasons it's going to act as a base. First of all, it's basic, right? And so it's not surprising that it's going to act as a base. Second of all, you can imagine that the oxygen is not going to be very nucleophilic because there are 3 methyl groups around it that are going to prevent it from really getting into tight spaces, right? And acting as a nucleophile. So instead of acting as a nucleophile, it'll act as a base, pull a proton from the carbon alpha to the electrophilic carbon. And that's going to result in loss of the leaving group and then formation of the product. Okay, and this is happening through a E2 bimolecular elimination, right? So you can see that the base and the electrophile or acid, right, are interacting in one step, right? So we need both of those things in there in order for this reaction to take place. Questions about this? Joey? Yeah.
It's probably unlikely, but would it be fair to say there'd be a small amount of product where the oxygen would act as a nucleophile to kick off like the chlorine or form like do that substitution?
So if we were using a different alkoxide, if you were using like methoxide or ethoxide, that's possible, but terbutoxide is such a poor
Just so,
nucleophile.
yeah, so much.
Yeah, so kinetically, it's going to be so slow to act as a nucleophile.
So not really a
Good question. Yeah.
Chlorine is not a good leaving group.
Chlorine is not a good leaving group. Well, it's not, I mean, it's not a great leaving group. It's a good leaving group, but it's not a
So
great.
in this condition, it can easily leave.
Pardon me?
Like, what would be the force that's pushing it out?
So in this case, it would be less likely to leave on its own. Yeah. And even if it did, right, we would still get to the same product.
But what is making it leave actually?
What is making it leave? So this carbon has 8 electrons around it, right? 2, 4, 6, 8.
Mm-hmm.
If we're taking these sigma electrons here, right, making a new bond to that carbon, we have to lose 2 electrons.
Okay.
Right? And those 2 electrons are going to be attached to the 5
My question is more like, why would that carbon prefer to have a double bond instead of, because the pi system stabilizes it.
So this
Over
double
the-
bond is now in conjugation with the pi system.
Exactly, yeah.
It's going to be
That's-
thermodynamically.